Welcome to class 7. So, today we will start by looking at what stress and strain tensors are. So, they would require some sort of special attention because they are actually higher ranked fields that higher ranked causes and effects that we apply and we measure on our properties. So, when stresses and strains are involved, when mechanics is involved, so you have degrees of freedom in several different directions, right. So, it is better to first understand what stress and strain is. Understanding an electric field, I just know it as V by D or dV by dl, right. So, it is a vector. Vectors are easy to understand, but tensors, right. So, we just need a simple formulation to see what stresses and strains are and what are the properties of these stress strain tensors, right. So, simple properties. Okay. So, first I will look at the stress tensor, and I said the stress tensor, so I represent it as xij, right. So, xij is x11, x22, x33, right, x12, x23, sorry, x13, x23, x32, x31, x21. Okay. So, this is the stress tensor. Now, we have so these are the shear stress components xij, where I is not equal to j is shear stress, and xii, these are not shear stresses, but these are sort of tensile and compressive stresses, right. So, these are stresses along the principal axis. Okay. These are normal stresses. Okay. So, in general, stress tensor is supposed to have 9 elements, but it does not. We will see why that is the case. But what is stress, right? So, how did people teach us what stress is? Stress is nothing but some sort of a force on an applied area. Right? So, if I have pressure is what is called homogeneous stress, right. So, sorry, pressure is isotropic stress. So, so pressure is just nothing but I have stress negative of it, but the stress is sort of isotropic in all directions. I do not have any shear components, right. So, this is the definition of pressure, right. So, so pressure is some case of stress, right. So, a particular case of applying stress to the material, right. So, now force and area, both of them have directions. So, as a result, stress turns out to be a tensor. Actually, you have to it's an involved proof to actually prove that stress is also a rank 2 tensor. I am not going to do it. If you want, you can refer to the book Nye, where it is proven that stress is a second rank tensor, and similarly strain is also a second rank tensor, but that requires some sort of mathematical proof. Here I am just going to argue that F has a direction, F is a vector, and 1 by A also has a direction in the along the normal vector of this area, right. So, I apply force on some area, right. Then the area of the face or whatever object I am looking at has a direction, right. So, that is the normal vector, right. So, force has a direction, normal vector has a direction. So, F by A, right. So, stress which relates x times A vector which has a direction x sorry, let me write it properly. So, stress relates force Fi equal to xij aj, right. So, this is so stress turns out to be a second rank tensor. So, it is okay. So, x is a second rank tensor. Now, let us look at an object. Let us do some applied mechanics for the next 10-15 minutes. Object which is under homogeneous stress. What does that mean? That means I have a huge object, right, and I take a very small volume and I call this so the representative volume element, right. So, this green cube that I have here, or the so yeah, so this one I will call this RVE, or a representative volume element. right. My object is this big and my object is under uniform homogeneous stress. So, every point in my object has the same stress, is experiencing the same stress, let us put it that way. And so I have so I am so if every point is undergoing, I take an arbitrary point, right. So, an arbitrary volume around a point, the point is the center of this representative volume element, and I am going to look at the stresses on those point with respect to this volume, right. So, this is my system of interest, right. So, the RVE or the representative volume element is the system of interest, right. Now, what does it mean to say that the RVE is undergoing is under homogeneous stress? What does it mean? It means that my surrounding material, right. So, if I have an RVE which is like this, my surrounding material is applying forces on my RVE, right. So, it is applying a force this way, it is applying a force this way, it is applying a force this way, it is applying a force this way. It is applying forces such that so the surrounding material is applying forces on the RVE such that RVE is in mechanical equilibrium. RVE is not moving, right, it is a rigid body, it is right there, right, it is neither rotating nor it is moving around, right. So, it is in some sort of a mechanical equilibrium. There is no flow, there is no flow in the system. Okay. So, there is homogeneous stress, none of these is a rigid body, a solid object, the solid object my RVE is not flowing with respect to anything, right. So, it is right there. Okay. If there is no flow, sorry, the top page, yes, then so okay, so how do I denote the stresses? So, for this I need to denote some axes. So, this is my RVE of interest, it is a small cube, right, so of equal sizes, right. So, A equal to B equal to C. So, if I actually look at so let me define again this to be my x2, my axis keep changing, this is x3 and this is x1. Okay. So, these are the axes and I will look at these two faces, right. So, this face and this face, right. Now, so let me look at the shear stress components, because the normal stresses, right. So, if I apply a force this way on okay. So, what about the normal let us do some force balance and moment balance, right. What about normal forces on this this is the point of interest, there is a face here, there is a face here. So, the rest of the material is applying a positive force on the on this face and this sort of a force on this face, right. So, then I can have force balance. So, this is F which is being applied in this direction, and this is minus F which is being applied in this direction. So, overall so this is so what I have on this face is F by A1, F1 by F3 by A3, this is A3, face A3, this is also F3 by A3. So, overall the sigma 33 is a constant, sorry. So, overall the material is under a stress which is sigma 33, but the forces are balanced. So, the material is not moving really. Okay. So, both these forces actually pass through the center point of interest. Okay. So, what however that is a trivial case, what I need to look at are the shear forces, right. So, let us say a force F3 is acting on face A2, right. Then the shear stress that I have is given as the sigma 32, right. So, that is force F3 acting on face A2, right. Now, there is an opposite force acting on face which is on the other side, which is on the back side, right. So, towards the positive side there are positive forces acting, and towards the negative side there are negative forces acting. So, that there is force balance, right. So, this F3 should be equal to minus F3, otherwise there is no force balance, otherwise the representative volume element will keep going up, right. So, it is under homogeneous stress, but it is under mechanical equilibrium. So, if there is a force here, there should be another force here, and these two forces should be balanced, right, and then there is no net force. Okay. So, sigma 3 2 is given as F 3 by A 2, right. All right. Now, there is force balance about this point if I look, right. So, about this point I have a force which is up here, but I have another force which is down here, right. So, the forces are balanced, net force is 0. What about the net moment, right? Because of force F3 on the face A2, these are the shear forces or shear stresses, right? I will get a net moment, right? So, the object then I have, this is my object, the object has a force this way and a force this way, right, and this will start rotating the object, right. So, it will start rotating the object in this direction, right. So, this is the anti-clockwise direction. Net moment, I will get a net moment in the anti-clockwise direction. Why am I getting a net moment? Because I have so I have a net torque, right. So, I have a net torque which is not balanced, right. So, so that so that moment is just so from the center I calculate the distance, is r, let us say. So, sigma 3 2 times A 2 times r, that is the moment, right. So, and then so there is, so this takes it up and this takes it down. So, you have a rotation, net rotation. Okay. Now, what about so this moment needs to be compensated somehow, right. So, how is it going to be compensated? If the F3, right, the force F3 is rotating it in this direction, I want a force on these faces which rotate it in the opposite direction, and that also exists, right. So, this force, if I actually look at force, that is the force in the 2 direction, so that is F2 acting on A3, right. So, the component, the moment I am looking at is sigma 2 3 A 3 times r, right. So, that is the magnitude of moment that I will get. Now, those forces will rotate the object in clockwise direction. I have a clockwise rotation. I am sorry, I keep using sigma for stresses generally, but in this course, because sigma has other connotations, I should be using an x. So, I will correct it here, but if I make a mistake I will try to correct myself. If I do not correct, then you have to assume that sigma is the same as x in context of stresses, right, because sigma is supposed to be conductivity in this course, right. So, I am looking at all different properties. Okay. Okay. So, what I have here is essentially x 3 2 A 2 r should be equal to x 2 3 A 3 r, right. R is the same, A 2s are A 3s are the same. We have this we have a cubic representative volume element. So, for this to be valid over all the points, right. So, I can take an infinitesimal volume about a point of interest, right. So, infinitesimal cube. For this to be valid about all points, I need this equation for moment balance, which is x 3 2 equal to x 2 3, right. Now, if x 2 3 equal to x 3 2, similarly x 1 2 equal to x 2 1 and x what is it 1 3 equal to x 3 1, right. So, all the shear stresses, right, they have to the transverse components I j should be equal to j I for moment balance, right. So, normal stresses it is anyway so they are balanced, right. So, you have a force balance in normal stresses, but shear stresses you have to balance the moments, right, otherwise the object will start rotating and flowing, right. So, that we do not want. So, as a result I have a next tensor now, which is a symmetric tensor. have x11, x22, x33, x12, x13, but I am just going to write x12 here, x13 here, x23 here, x23 here, right. So, because of this moment balance that I did, right. So, so this is quite, I mean, so if you are a mechanical engineer, you would have done this in one of your strength of materials course. This is something very standard. So, under homogeneous stress, you have a stress tensor which is symmetric, right. So, you always have a symmetric stress tensor. So, that is what we are going to use in this course. Our stress tensors are always symmetric, right. So, how many components can be there, independent components can be there in a stress tensor? They are 6, right. So, if I have xij, I will write it as sorry, I have already written it. So, since I have 6 components, the way I will write each of these components is I will write this as I will write them just with one index, but this index will move from I equal to. So, instead of writing it as 2 indices, I am going to write it as one index, which is going to run from xi or xk, xijk, okay. So, xk, but this index is going to run from 1 to 6, right. So, x1, x2, x3, x12 will be x6, x13 will be x5, x23 will be x4. So, if there is x4 here, there is x4 here, there is x5 here, and there is x6 here, okay. Now, so essentially what I said is if there is x12, I am going to represent it as x5, right. So, or so the notation I used is 11, 22, 33, this is 1, this is 2, this is 3, right. 1, 2, this is sorry, let me start with 2, 3. 2, 3 is an index that I will write it as 4. 1, 3 is an index, I will write it as 5, and 1, 2 is an index, I will write it as 6. This is a standard convention, okay. So, this writing a second rank tensor as a sort of a 1 by 6 sort of a notation, right. So, xij writing it just with one index, but this one index has 1 to 6, so it can k can go from 1 to 6, right. So, this sort of a transform a notation is what is called Voigt notation, right. It becomes easier, right. So, you reduce the number of components in this tensor, so the dimensionality sort of reduces, it becomes easier for you to calculate, etc. So, Voigt notation is can be used for, I mean, so sometimes it eases the calculations that you do. So, that is why people use Voigt notations, right. So I mean, I can just say, okay, I have a stress tensor xk, but that doesn't mean I have a first rank tensor. Right, I am sort of representing a second rank tensor as an array of 1 by 6 array, right. So, it's a vector of higher dimension in some sense, right. So, it does not mean that I have a vector, but I am sort of cheating it a bit, and then I am for the ease of mathematics I am just representing it as one index, okay. Okay, that is about stress. What about strain? Strain tensor, right. Now, what is strain, right. So, if I have a point P, right. So, PQ is my Q1, this is Q2, right. This is my entire object. So, this is the x1 axis, this is the x2 axis, right. So, this is I am going to do it in 2 dimensions, right. So, this is my entire object. Now, I am going to say that the object has strained, right. So, this is before strain, right. By the way, so our traditional definitions of strain, so you say strain is nothing but delta L by L, or so delta L, if I have to talk about shear strains, delta L2 by L1, that sort of a thing, right. So, the change in length per unit length, that's that is the strain, right. Now, after straining this material, the point P goes somewhere here, let us say, let me draw it in black. So, this is P dash, right. The point Q 2 goes somewhere here, that is Q 2 dash, and the point Q 1 goes that also sort of deforms a bit, right, and then goes here, Q 1 dash. So, this is what strain has done. So, I have taken 3 points, one of them is sort of a reference point, and with respect to reference point I have taken 2 more points Q 1 and Q 2, and I am following their trajectory, right. So, this is following the trajectory upon straining. Of 3 points in the object. Upon straining, right. So, Q 1 goes to Q 1 dash, Q 2 goes to Q 2 dash, but this entire P Q Q 1 Q 2 that sort of an L shaped object now deforms into something else, right. So, deforms and also moves, right. So, into something else. Okay. So, now we can define what is strain in this case, right. So, let us we can take a component. So, this was the original length of P q, right. So, that is my, so the length of P q is delta x 1, let us say, length of this is delta x 2. So, this is my, to start with delta x 1, but it has extended because I have strained it, I could have deformed it, I could have extended and also rotated it, right. So, that is strain essentially. So, and then this is delta u 1, right. So, I want to look at what delta u 1 is. Delta u 1 is nothing but dou u 1 by dou x 1, right. So, this is in the differential form times delta x 1, right. So, now this dou u 1 by dou x 1, I am going to define this as E 1 1 delta x 1, right. So, dou u 1 by dou x 1 is the displacement I get per unit length, right. So, the differential displacement I get per unit length. This is not yet strain, but this is something that I call a deformation tensor. I am going to define a deformation tensor first, right. So, strain is a part of that, it is not really a deformation tensor. So, what do I have? I have delta u 1 E 1 1 x 1 sorry delta x 1, that is equal to dou u 1 by dou x 1 times d delta x 1, right. Now, if I go back, right. So, there is a delta u 2 also, right. So, so the object did not just move this way, but it also has moved this way, right. So, there is a delta u 2, okay, with respect to x 1. Now, delta u 2 equal to E 2 1 delta x 1, right, where E 2 1 is dou u 2 by dou x 1 delta x 1, right. All right. So, I can define E 1 2 and E 2 2 analogously by looking at the vector x, the other vector and how it has deformed, right. So, I have in 2 dimensions I have defined what is called a deformation tensor, which is E 1 1, E 2 2, E 2 1, E 1 sorry E 1 2, E 2 1. Okay. Okay. Now, that is nothing but it is just the differential forms of displacement dou u 1 by dou x 1, So, I have an initial length and how much am I stretching in the same direction, that is dou u 1 by dou x 1. I have an initial length, but with respect to the initial length in the one direction, how much am I displacing in the other direction, right. So, that the differential displacement divided by dou this is dou u 2 by dou x 1, this is dou u 1 by dou x 2, this is dou u 2 by dou x 2, right. So, these are the definitions of the deformation tensor. Okay. Now, instead of deforming, so I can deform the material in any way I want, right. So, I can shear it, I can do whatever, but instead of doing any form of deformation, what I am going to do next is I take my my P Q 1 Q 2, right, which is at 90 degrees with respect to each other, and I take it to a different location and I am just going to rotate it, right. So, I am not going to do anything else. This is the transformation is just rotation, rigid body rotation, right. Okay. I have to be a bit more careful because these lines I do not want them to be parallel to each other. So, let us draw it again. So, here I am going to draw a rotated object with So, right. So, this is P dash, this is Q 1 dash, this is Q 2 dash, and the only difference between P Q Q 1 and P dash Q 1 dash Q 2 dash is P dash Q 2 dash is rotated with respect to this, right. So, it is just a rigid body rotation. Right. Now, if I ask you, so in case of rigid body rotation, right. So, this it rotated by an angle phi, let us say. So, phi, what is okay. So, this is I've sort of exaggerated this, the strains are not going to be so large. So, we do not, or the rotations, right. So, it is a small phi, right. So, I am just going to rotate it by a very small phi, and that is the object. Okay. So, the phi is small, right. So, this is the initial length delta x, right, and then this is my delta u, okay, after rotation. So, tan phi is nothing but delta u by delta delta u 2. I have to follow the directions properly, delta x 1 plus delta u 1, but delta u 1 is very small compared to delta x 1. So, I am going to as well ignore that. So, tan phi is just delta u 2 by delta x 1, or in that fashion phi is nothing but delta u 2 by delta x 1. Okay. Now, this is so I have, let us say I just did a rigid body rotation. So, if I did a rigid body rotation and I ask you the question, what is the transformation matrix for a rigid body rotation? What will you tell me? It is nothing but 0, 0, minus phi, phi, right. So, this is how so a point q 1 we would have transformed just under rotation, right. So, this is how a point q 2 would have transformed just under a very small rotation. Okay. So, this is this tensor I am going to call it the delta tensor, okay, just for rigid body rotation, and we know that phi is nothing but 0 delta u 2 by delta x 1 minus of that delta u 2 by delta x 1 plus of that and 0, right, or the other way around, right. So, in that sense so delta u 2 by delta x 1, if I am just rotating, that is nothing but my E 2 1, right. So, when I am doing rigid body rotation, all I have is the deformation components, which are E 2 1 or E 1 2, sorry, these two are identical. I will just write it as E instead of E 2 1 or E 1 1. So, E, E and 0, right. So, the rigid body, so in the deformation, right. So, when I am doing deformation, right, the rigid body component of the rigid body rotation component of deformation is an antisymmetric tensor. Which means my delta is so minus E and 0, right. So, or A transpose equal to minus or delta transpose equal to minus delta, right. So, if I sorry, in other words, let me put it this way, delta ij, what is meant by antisymmetric tensor, delta ij equal to minus delta ji, right. So, delta 1 2 equal to minus delta 2 1, that is what is happening here, whereas delta 1 1 equal to delta 2 2 equal to 0, right. So, that is the property of an antisymmetric tensor, right. So, antisymmetric tensor of my deformation is nothing but a rigid body rotation. Okay. Now, I have a deformation tensor which is E11, E12, E21, E22, right. So, when I deform the material, I can rotate it, I can stretch it and do all sorts of things, right. Everything does not account to straining the material, right. So, for straining the material, what I should do is I should remove the rigid body rotation component and only the deformation, only the stretching and so deformation minus rigid body rotation is strain. Okay. So, that is where I am going to come to. So, from this, right, so this I am going to write it as a symmetric tensor plus an antisymmetric tensor. Because I know that the antisymmetric tensor corresponds to rigid body rotation. And the symmetric tensor corresponds to strain, right. So, by definition, just the symmetric part of the deformation tensor is strain. Okay. All right. So, E then will be equal to I am going to say so I am going to split it as a symmetric tensor. So, for symmetric tensor I will have E11, E22, blah, but I have here half E12 plus E21 and here I have half E21 plus E12 again, right. So, these two components are equal, right. So, that is a symmetric tensor plus an antisymmetric tensor where these two components are 0, but here I have half E12 minus E21, whereas here I have half E21 minus E12, right. So, this is like my delta, right. So, the rigid body rotation 0 minus phi phi 0, whereas this is my strain tensor. So, instead of writing it as so I am going to write it as x11, x12, x12, x22, right. So, just by definition, by defining strain, as the non rigid body component, rigid body rotation component, of the deformation tensor, right. So, I have strain tensor now, the small x I j becomes a symmetric tensor, right. I sort of cheated, I mean, so strain is not exactly dou u by dou x1 or dou u by dou x2, that is the deformation, but from the deformation tensor I remove the rigid body component and then I get the strain tensor, right. So, so by definition I am making my strain tensor as a symmetric tensor. Okay. So, by definition strain tensor is a symmetric tensor. It also makes sense, right. So, if I take an object and just rotate it, I am not straining the object, I am just doing a rotation, right. So, in any sort of deformation, if I sort of stretch it, pull it and rotate it, I have to remove the rotation and then the rest of it is called straining the material, right. So, I am straining the material in some sense. Okay. So, you can also extend this idea to 3 dimensions, strain is going to be a symmetric tensor x22, x33, x12, x12, x13, x23, x13, x23, right. And since strain is a symmetric tensor, I can also use the Voigt notation to denote strains. So, the Voigt notation looks something like this: x1. Here one needs to be a bit careful. The way I will define my x5 is, you know, it will make sense later on when I do piezoelectricity. In this course I am going to define x12 as half of x6, okay, and x13 as half of x5, x23 as half of x4, right. So, I have half of x4 here, I have x3, x2, half of x6 here and half of x5, right. So, there is a half factor that adds in which is different from stress, but that would require an explanation of, you know, because I am writing stresses and strains to explain piezoelectricity, right. So, so when I do piezoelectricity it will make sense why I put a half here, but I will come to that in the later part of the course, okay. So, for now just take it for granted that I have a half coming in here, okay. Now, the last thing that I will do is, alright, so I have a polarization Pi equal to what was it, Dijk times sigma jk, right. So, this is my piezoelectric effect, right, and piezoelectric tensor. But now I am going to write you know, so okay, so let me expand this, right. So, let me just write what Pi is. So, Pi is d I 11 sigma 11 plus d I 22 sigma 22 plus d I 33 sigma 33, right, plus d I 12 plus d I 21 sigma 1 to 1, right, but 1 to 1 is the same as sorry, what am I doing? Sorry, sigma 1 2, but sigma 1 2 is the same as sigma 2 1. So, you know, so I can combine these two terms, plus sigma 2 3, again I will have d I 2 3 plus d I 3 2, right. So, I am using the fact that sigma 3 2 is the same as sigma 2 3, the symmetric nature of this tensor, plus d I what is it, next comes sigma 1 3. So, 1 3 plus d I 3 1, right. Okay. Now, while doing piezoelectricity I am going to define this, right. So, as you know, sigma 1 1 was defined as sigma 1, sigma 2 2 was defined as sigma 2, sigma 3 3, I am going back to Voigt notation as sigma 3, sigma 1 2 is nothing but sigma 5, sorry, sigma 6, sigma 2 3 is nothing but sigma 5, and sigma 1 3 is nothing but sigma 4, right. So, now I want to write my Pi as just a you know, d I k times sigma k, right, where sigma k. So, this is like I am writing you know, a second rank tensor, like I am writing a second, dik is a second rank tensor, like sigma k is a first rank tensor, except that k has an index that goes from 1 to 6. So, in the Voigt notation I want this equation to be satisfied. So, for this equation to be satisfied I need my d I 6 for example to be equal to d I 1 2 plus d I 2 1, right, or you know, so there is no way of separating d I 1 2 from d I 2 1. So, that is just 2 times d I 1 2 or d I 2 1, right. Similarly, d I 4 will be equal to d I you know 2 3 plus d I 3 2, that is 2 times d I 2 3, okay, and d I 5 will be d I 1 3 plus d I 3 1, that is 2 times d I 1 3, okay. So, in general, right, so piezoelectric tensor in Voigt notation, right. So, then this let me finish it by saying then if I have these sort of definitions right. So, from Voigt point of view d I 1 is just d I 1 1, d I 2 is just d I 2 2, right. I goes from and d I 3 is just d I 3 3. I goes from 1 to 3, but k can go from 1 to 6, right. So, that is my Voigt notation. So, in general if I just to finish, right. So, the piezoelectric coefficient can be written as I k, where I goes from 1 to 6, sorry 1 to 3 and k goes from 1 to 6. Why am I able to use Voigt notation in the first place? That is because Voigt notation makes sense. I am able to use it just because sigma I j is a symmetric tensor. Okay. So, since sigma I j is a symmetric tensor, I could use Voigt notation to explain piezoelectricity, and if I calculate the number of independent components without doing any symmetry operations, right. So, number of independent components of d I j k, which is nothing but so I can write it as d I L, where I goes from 1 to 3 and L goes from 1 to 6. It is 3 times six. So, I have 18 components, right. So, what were supposed to be 3 times 3 times 3, right. So, if I leave it as a second rank tensor, third rank tensor, I am thinking of having 27 components, but just by saying that stress is a symmetric tensor and I would come to Voigt notation and then use that symmetry, right. I can reduce the number of components of piezoelectric tensor from 27 components to just 18 components. Okay. So, there is some reduction in the, so I do not need to calculate all the, I do not need to measure all 27 components to understand the piezoelectric nature of my material. I could start with 18, right. So, 18 is still a daunting number, I would still reduce it by using material symmetry from next class onwards, but so just using the properties of stress and strain as field tensors, I can reduce the number of components of a piezoelectric tensor. Okay. So, with that, let me quickly summarize that we have seen what the stress tensor is, what the strain tensor is in this class. We have seen how stress tensor, both stress tensor and strain tensor are symmetric tensors, and so later, since they are symmetric tensors, we could use a Voigt notation to look at stress and strain as sort of pseudo vectors, not really tensors, but pseudo vectors, right. So, but a 1 by 6 vector, not a 1 by 3 vector, right. And this 1 by 6 vector, so you can also propagate this the simplicity in mathematics using Voigt notation into the piezoelectric tensor, where now we should just worry about 18 components of a piezoelectric tensor if I am not using any material symmetry ideas yet. So, 20, I do not need to worry about all the 27 components, which seems daunting. I reduce it to 18, right. So, from 18 I am going to reduce it to much further, so I am going to reduce the number of components much further by using ideas of material symmetry, right. So, in the next class we will start with material symmetry. Okay. All right, thank you. See you in the next class.